Hi, I'm Dr. Tom Calabrese, and welcome to this installment of Insights into Computer Science. This week, we will be looking at how logic constructs can help us better control decision-making in our program solutions. But first, let's review. There are four kinds of control structures that are commonly used in programming: iterative, or counting our way through a loop; sequencing, that is, creating specialized functions or subroutines that cause a change in our program flow so that we can reuse code and make our programs more efficient; selection, our ability to make choices on whether or not to execute a block of code based on a condition. This is where we find things like if, then, else statements. Conditional, similar to the selection statement, except that we remain in a loop, a while loop, as long as the condition is met. It is these last two control mechanisms that are of interest to us today. You see, both of these control mechanisms are governed by a condition that cause us to choose whether or not to do the action in a control block. These conditions can be things like if the variable x is the value 5 written as x = 5. Remember, the double equal sign means a test for equality and is very different than the single equal sign, which means to assign. Another condition might be x is greater than or equal to 5, or y equals the string ABC, or simply true, which means that we always do something, or false, which means that something will never happen. In a selection statement, we would use these conditions to control which code gets executed. So, if a condition is true, then perform some actions. Else, meaning if the condition is not met, perform some different actions. These conditions are very important in programming and make a nice addition to our toolkit. Notice, though, we are using outcome statements like if a condition is true or if a condition is false. These true-false statements are what we want to talk about today. These are known as Boolean logic. Named after the 19th century mathematician George Boole, who wrote about this in his papers An Investigation of the Laws of Thought, created in 1854. Boolean logic is a form of algebra in which all the values are reduced to either true or false. Boolean logic is especially important for computer science because it fits nicely with the binary numbering system in which each bit has a value of 1 or 0. Another way of looking at this is that each bit has a value of either true or false. The standard is that 0 means false and 1 means true. In computer science, there are two types of logic: relational and bitwise. Relational logic is what we've been talking about so far. Take two values or variables, or results to be more specific, and compare them relationally to develop a true or a false condition. It's really pretty simple. The relational operators in the Python programming language, for example, are the less than sign, the less than or equal to sign, the greater than sign, the greater than or equal to sign, the double equal sign, meaning compare for equality, and the exclamation point equal, which means not equal. If we use these relational operators, we cause the computer to generate a true or a false outcome. So if you're running a program and somewhere in that program the value of x is set to 5, let's say, then later in the program the value y is set to 10. If we then make the comparison, if x equals y, meaning to test for equality, this would cause the computer to generate a false, so the condition is not met and the code is not executed. However, if we said instead x not equal to y, this would generate a true, because 5 is not equal to 10, and so the statement, in fact, is true. This can sometimes be quite confusing. Consider this problem. I have 5 questions that are true or false. The answer to this statement, number 1, is the same as the answer to statement number 5. The answer to this statement is different from the answer to number 3. The answer to this is the same as the answer to statement 4. The answer to this is the same as the answer to statement 2. And 5, the answer to this is different than the answer to statement 1. This is the interrelationship of true-false outcomes. So why not pause the video and see if you can figure it out? Okay, that is a mess, or so it seems. So let's quickly work through it. First of all, isolate statements 1 and 5 as being interdependent. If statement 1 is true, then statement 5 would have to be true, but that would be wrong, since to be true, it would have to be different from 1, so that can't be the answer. If statement 1 is false, then statement 5 would have to be true. Well, what do you know? This is correct, since true is different than false. Statements 2, 3, and 4 are related in a similar way. If statement 2 were false, then 2 would have to be equal to 3. 3 would then have to be false. That would mean 4 would have to be true, but that can't be right since true is not the same as false. So, if 2 is true, 3 would likewise have to be false, and it would not be equal to 2. That means that 4 would have to be true, and in this case, it would be the same as 2, and the logic works. So the correct answer is false, true, true. So what's the point of all this? Well, I guess one point is that true-false tests are not as easy as they may seem. But more importantly, combining logic, where one logic statement depends on another, can allow us to create complicated conditions. This can be really useful in programming. In programming, we do this with logic operators, not, and, or, and exclusive or. Not just makes true false and false true, as we saw earlier. For the rest, we need to look at what are known as truth tables. A truth table takes a pair of hypothetical conditions, let's call them A and B, and the truth table applies the logic expression and tells you the result. Let's look at the truth table for a logical AND. When A is false and B is false, then A logical AND B is false. When A is true and B is false, then A logical AND B is false. When A is false and B is true, A logical AND B is false. But when A is true and B is also true, then the result of A logical AND B is true. Let's take an example. Say A is that you are accepted to Johnson & Wales University, and B is you have access to money to pay for it. So your own money, loans, scholarships, whatever. Let's then examine our truth table. If you are not accepted, or A is false, and you have no money, B is false, then you cannot attend school. A logical AND B is false. If, however, you are accepted, A is true, and you have no money, B is false, then you cannot attend school because A logical AND B is false. If you are not accepted, but you have money, B is true, then you cannot attend Johnson & Wales because A logical AND B would also be false. But if you have been accepted, A is true, and you have access to money, B is true, then you can attend Johnson & Wales University because A logical AND B would be true. The OR truth table is different and is much more forgiving in a Boolean sort of way. If A is false and B is false, then, as you might expect, A logical OR B would be false. If A is true and B is false, then A logical or B is true. If A is false and B is true, then A logical or B is true. And of course, if A is true and B is also true, then A logical or B is true. Suppose that A is you have your own money, and B is that you have access to other money, say a loan or a scholarship. Then we can say, if you have no money, A is false, and you have no access to other money, B is false, then you can't go to school because A, logical or B, is false. If you have money, A is true, and you have no access to other money, B is false, then you can go to school because A, logical or B, is true. If you have no money of your own, A is false, but you do have access to other money, B is true, then you can go to school, A, logical or B, is true. Finally, if you have some money, A is true, and you have access to other money, B is also true, then you can pay for school, A, logical or B, is true. Last but not least is the exclusive or. One or the other is true, but not both at the same time. If A is false and B is false, then A XOR B is false. If A is true and B is false, then A XOR B is true. If A is false and B is true, then A XOR B is true. But if A is true and B is true, then A XOR B is false. Let's say you don't like plain milk, but you will drink strawberry or chocolate milk. Then we can examine a truth table to see whether or not you will drink what I put in your glass. If A is chocolate syrup and B is strawberry syrup, then if I do not add chocolate syrup, A would be false. And if I do not add strawberry syrup, B would be false. But then it would be plain milk, and you don't like that because A XOR B is false. If I add chocolate syrup, A is true. And if I don't add any strawberry syrup, B is false. Then what you have is chocolate milk, and you will drink that because A XOR B is true. If I do not add chocolate syrup, A would be false. But I do add strawberry syrup, making B true, then you have strawberry milk, and you will drink that because A XOR B is true. But if I add chocolate syrup, A is true, and I squeeze in a little strawberry syrup, B is also true, that would be disgusting. So you probably won't drink that because A XOR B would be false. So let's see how we can apply these concepts to computer logic by allowing statements with complex compound logic, like, suppose I have three conditions as determined by relational statements. A is true, B gets a result of false, and C is true. If I use the following selection statement, if A and B or A and C, then execute the code, we can see that A logical and B would produce a false, but A logical and C would produce a true. Now, if we examine our truth table, a false logical or true is true. So this condition is evaluated as true, and the code would in fact execute. Let's try a conditional statement. While A or B and not A or C, then execute the code. In this case, A or B is true. A or C is also true, but then we have to use the not, that which would make that false. So a true logical and false is false, so our condition is false, and that code would not execute in this case. This sort of logic juggling can allow us to make some really interesting complex conditions and allow our programs to make very difficult decision choices. So as you can see, this week we have explored a really important concept in computer science. But put another way, if you understand the difference between true and false, and you understand the logical and truth table, and you understand the logical or and understand logical exclusive or truth tables, and you understand the importance of the logical not, or you plan to pay somebody else to do your programming, then have a great week. I'll see you next time. Else, it might be a good idea to watch this video again. But until next time,